Okay, hello and welcome back. In this video, we are covering section 11.5, which is on partial fraction decomposition. So to help describe what this is, I want to first look at what we would need to do if we wanted to combine these two fractions. Let's say we had 3 over x plus 4, and we want to add this to 2 over x minus 3. Well, in order to combine these two fractions, we would need a common denominator. So one thing we can do is multiply each fraction by the denominator of the other fraction on the top and bottom. So like for our first fraction, 3 over x plus 4, we can multiply that by x minus 3 in both the numerator and the denominator. So we'll have x plus 4 times x minus 3 in the denominator. And then we'll do the same for the second fraction. So let's multiply that one by x plus 4 on the top and bottom. So that would be 2 times x plus 4 over x plus 4 times x minus 3. So now they have a common denominator, so we can add the two fractions together. So we'll have one fraction. I'm going to go ahead and distribute in the numerator. We should have 3x minus 9 plus 2x plus 8 all over x plus 4 times x minus 3. And then we would combine like terms, and we would end up with 5x minus 1 over x plus 4 times x minus 3. So in partial fraction decomposition, we're going to do this process in reverse. We're going to start with something like what we have here. So some fraction with maybe some polynomial in the top, and in the bottom we have some factors that are multiplied together. And we're going to end up splitting this up into two separate fractions where these previously multiplied factors in the denominator now show up as separate denominators for each fraction. So we are decomposing it into multiple fractions, where we then have some numbers on top that we'll need to find out how to produce. So that's what we'll be doing in this section. We'll be splitting up or decomposing a single fraction with some factors in the denominator into multiple fractions with those factors split up. So we'll see a few different cases. We'll start with our first case, which is called having non-repeated linear factors. So let's look at the example first, and then we'll come back to this general statement here. We can just start with example 2. So we're given x over x squared minus 5x plus 6. We don't see any factors yet. We need to factor the denominator. So I would be looking for factors of 6 that add up to negative 5. That should be negative 3 and negative 2. So that denominator will factor into x minus 3 times x minus 2. So this is the condition of having non-repeated linear factors. They're linear because we don't have any quadratics, we don't have any x squareds in these factors, and they're not repeated. What it means by a repeated factor is if we had maybe a power, like the third power, or even the second power, that means we have multiple copies of those factors. So they're all to the first power and they're all linear. If that's the case, then this should split up into, in this case, two fractions. So one fraction that will have x minus 3 in the denominator, and another fraction that will have x minus 2 in the denominator. And they'll have something in the numerator. So I'm going to write just generally, this will be something that I'll call a, and something that I'll call b. So we need to try to find out what a and b should be equal to in order to make this statement true, that the left side is equal to the right side. So there's two different approaches. I'll show one and then the other, and then we'll end up doing kind of a combination of the two. But they both start out the same. The first thing I'm going to do is to multiply both sides of this equation by the denominator on the left side, that common denominator. So I'll write it out explicitly first. I'll place it in the numerator of every element here. So this will give me x times x minus 3 times x minus 2 over x minus 3 times x minus 2. So we'll see that those will cancel. Then I'll have a times x minus 3 times x minus 2 over x minus 3 plus b times x minus 3 times x minus 2 over x minus 2. So notice what will cancel. On the left side, everything will cancel. For our a term, the x minus 3's will cancel. And for the b term, the x minus 2's will cancel. So we're left with just x equals a times x minus 2 plus b times x minus 3. We've essentially just cleared all of the fractions by multiplying the entire equation by our common denominator. So now I'm going to distribute a and b. I can write this as a times x minus 2 times a plus b times x minus 3 times b. And then I'm going to group my like terms together. Like I'm going to put ax and bx together, and then minus 2a minus 3b. So on the left side, I have just x, and I can write this as x plus 0, and we'll see why in a second. On the right side, on those first two terms, I can factor out an x, and I'm going to place the x on the right side to view this as a coefficient. I would just have a plus b inside times x. And then I'm going to say, well, plus some other term that's composed of minus 2a minus 3b. So the reason I'm doing this is we can now make a couple of statements by comparing the left side and the right side. The coefficient of x on the left side is 1, and it's being added to 0. And this is supposed to be equal to the right side. So if these two sides are equal to each other, then the coefficients must be equal. If this is 1x, then a plus b in front of that x should equal positive 1. And it's being added to 0, so that means all of this, the minus 2a minus 3b, should ultimately cancel out and just become 0, because we're saying that this should all reduce to the left side. So minus 2a minus 3b will be equal to 0. So now we have a system of two equations that we want to solve in order to find out what a and b are equal to. So we can do this via substitution or elimination. I'm going to do substitution. Let's solve the first equation for a. I can say that a equals 1 minus b. So then let's plug that in for a in the second equation. So I can write this as minus 2 times a, so minus 2 times 1 minus b minus 3b should equal 0. Now we can solve this for b. Let's distribute the negative 2. This becomes negative 2 plus 2b minus 3b equals 0. So I'll add the 2 over. 2b minus 3b is negative b equals positive 2. So that means b must be equal to negative 2. So that's one of our unknowns that we needed to find. So let's go back to our first equation, plug in negative 2 for b. Should have written a negative here. So in our first equation, we can say that a should equal 1 minus negative 2. So that means a is equal to 3. So let's plug these into our original statement up here. We said this should split up into these two fractions. So we can say x over x squared plus 5x plus 6, that was our left side, should equal, our a value is 3, over our first factor, x minus 3, minus 2, over our second factor, x minus 2. Because our b value was negative 2, so we can write that as a subtraction. There is a second approach that we can take starting from this point. So I'm going to copy down that line here. We have x equal to a times x minus 2 plus b times x minus 3. So if this is an identity, if this is true, if these are equal to each other, it must be true for all values of x, which means that we can choose some particular values of x that might cancel out one of our unknowns, a or b, and allow us to solve for the other one. For instance, notice if we plug in positive 2, that will essentially delete the a term and leave the b term. So I can say when x equals positive 2, let's plug that in for every value of x. That would give us 2 is equal to a times 2 minus 2 plus b times 2 minus 3. So 2 will equal 0a minus 1b. And this gives us our b equal to negative 2. And we can do the same thing for our b term. If we plug in positive 3, that will allow us to solve for a. So I'll say when x equals positive 3, this will give us 3 is equal to a times 3 minus 2 plus b times 3 minus 3. So 3 equals 1a plus 0b. And that gives us our a value of 3. So this way is kind of nice because we avoid having to do a system of equations, which can become a little bit tricky. But I will say this won't always work all of the time. There might not be some numbers that we can plug in that will allow us to solve for all of our unknowns. But what we can do is a kind of a mixture of these two methods. So I'll first typically try this method of just plugging in some values. And then if there's anything that remains that I'm not able to find out using this method, then we can take that first approach with the numbers that we've already found in mind, and that can allow us to solve it a bit more quickly. So this was the example of having non-repeated linear factors. In that case, we just split it up into separate fractions where we just have some number, some unknown in the numerator with each factor in the denominators. So this box gives us the general situation. So they're looking at p of x over q of x. That's just saying we have some polynomial in the top and the bottom of a fraction. And this is a case where q of x is some multiplication of linear factors. And they're just writing these general terms. So however many you have, it just splits up into separate fractions, and they're using a1, a2 up until an, meaning however many you have. So you get just a series of fractions added together with your factors separated into each of the denominators and some unknowns in the numerator. So for us, we had x over x minus 3 times x minus 2. It splits up into two fractions with x minus 3 and 1 with some unknown a in the numerator, and then x minus 2 in the other one with some unknown b. So from there, just to give the overview again, we multiplied by the denominator on the left, so that will cancel a lot of the terms, and we arrive at like a flat equation like this, where we don't have any fractions. At that point, I would suggest trying to first just pick some values. As we did in the second case, you can see it was a lot quicker than the first method. But again, we may be forced to use this first method if there aren't any good numbers to choose. And we'll see some examples of that. So let's take a look at the second case. This is whenever we have repeated factors. So again, let's look at the example and then we'll come back to the general statement. So this time we have x plus 2 over x cubed minus 2x squared plus x. So we don't see any factors yet, so we need to do some factoring in the denominator in order to see what we have. It looks like first we can factor an x out of every term. So we'll be left with x squared minus 2x to the first power plus 1. And then we can factor x squared minus 2x plus 1, two factors of 1 that add up to negative 2 are negative 1 and negative 1. So that means we have a repeated factor, x minus 1 will appear twice. So we can write that as x minus 1 squared. So this is a case of having a repeated linear factor. We still have a non-repeated one, but this one is repeated 2 times. So this will give us something that looks a little bit different. For that first term x, we'll just get a over x. For the second term, we'll have b over just x minus 1 to the first power. And then we will get a third fraction, so I'll have to say plus some unknown c over x minus 1 squared. So if you have a repeated linear factor, you have to build up to the power. In this case, we had the second power, so we get two terms, one with the first power and then one with the second power. If this was, say, like the third power, then we would get plus another unknown over x minus 1 cubed. So you just build up to whatever power you have. In this case, we just had the second power. But if it was, say, like the fifth power, you would have 5 terms where each denominator increases by 1. The power will increase by 1. From this point on, the process will be the same for each of our cases. So the difference is really just in the setup. So let's continue as we did before. Let's imagine that we're going to multiply this denominator on the left side by every term on both sides of the equation. So it'll completely cancel on the left side and we'll be left with just x plus 2. When we multiply by this first term, the x's will cancel and we'll be left with the x minus 1 squared. So we'll have a times x minus 1 to the second power. For our b term, when we multiply by x times x minus 1 squared, it will pick up that x, and one of the x minus 1's will cancel, So there should just be 1 left over. And then for the c term, the x minus 1 squared will cancel and we'll be left with just x. So we multiplied by the denominator on the left side and canceled wherever we can. If you need to write out the full multiplication like we did last time, um, definitely go for that. It takes a few times to start to get used to the pattern. So from here, I'm going to first try to just plug in some values for x that will allow us to find out what some of our values should be. Like notice if we plug in 0, it will delete the b and c term and preserve the a term. We'll be able to solve for a. So I can say when x equals 0, on the left side we'll have 0 plus 2, so just 2, will equal a times 0 minus 1 squared plus b times 0 minus 1, that term will just become 0, plus c times 0. And then negative 1 squared is positive 1. So this tells us that a is equal to 2. So let's come back and see, is there another number we can plug in that will delete 2 terms and leave 1? And it's useful just to look at these factors. It looks like a and b both have a shared factor of x minus 1. So if we plug in positive 1, it should delete the a and b term and keep the c term. So let's do that. I can say when x equals positive 1, that'll give us 1 plus 2 on the left side. So we'll have 3 will equal a times 1 minus 1 squared, so 0a, plus b times 1 times 1 minus 1, so that will give us b times 0, plus c times 1. So we get that c is equal to 3. So we have a and we have c, and we need to find b. We don't have a nice number that we can plug in that will cancel both a and c and leave b. However, since we do know what a and c are equal to, we can plug that in and then just choose some other value of x. So let's say maybe when x equals positive 2. Let's plug that in. I'll say x is equal to positive 2. And also, we know that a is equal to 2 and c is equal to 3. So on the left side, that gives us 2 plus 2, so that'll be positive 4, will equal a is equal to 2 times x minus 1, so this will be 2 minus 1 squared, plus b times x, so b times 2 times 2 minus 1, plus c times x, that will be 3 times 2. So notice all that remains is b, and we can just clean up the rest of our terms and solve for b. This is 2 times 1 squared, so 2 plus 2b times 1 plus 6. So 4 equals 2b plus 8. Let's subtract the 8 over. 4 minus 8 is negative 4 equals 2b. So dividing both sides by 2, we get that b is equal to negative 2. So when there's only one unknown remaining, if you found everything else, you can plug those in and then just choose some other value of x. So let's write out our solution. We started with x plus 2 over x times x minus 1 squared equals a over x, our a value is 2, so 2 over x, plus b over x minus 1, so we'll have negative 2 over x minus 1. We could really write this as a subtraction, since the 2 is negative, plus c, so our c value is 3, over x minus 1 squared. So whenever you have a repeated factor, and specifically we have a repeated linear factor, repeated again just means that we have a factor to some power greater than 1. Let's take a look at their general statement. They're saying we have some linear factor x minus a to some power n, where n is greater than or equal to 2. Then we split that up into separate fractions where we build up to the power. So they're just saying this is some general power of n. So we would have our first fraction with x minus a to the first power, then x minus a to the second power in a second fraction. And this continues until we reach whatever the level of our original power was. So in our case, we had, after doing some factoring, the x minus 1 squared. So we got one fraction with x minus 1 to the first power, and then a second fraction with x minus 1 to the second power. Then once we have the setup, the rest of the process will be the same. So this time we were able to avoid any system of equations just by choosing values of x and plugging in our knowns once we have those figured out. Okay, our next situation is when we have what's called a non-repeated irreducible quadratic factor. So again, let's look at our example here. We have 3x minus 5 over x cubed minus 1. So x cubed minus 1, we'll have to see that as a difference of cubes, and we do have a factoring formula for that. Let me insert that here. If we have something like a cubed minus b cubed, this will become a minus b times a squared plus a times b plus b squared. There's a similar one for a sum of cubes. If we had a cubed plus b cubed, this factors into a plus b times a squared minus ab plus b squared. So you can multiply out the right side just to verify that we get the left side, but these two identities are true for the sum and difference of cubes. So what we have here is x cubed, technically minus 1 cubed. So let's use this pattern to factor the denominator. We will have 3x minus 5 over x minus 1 times x squared plus 1 times x plus 1 squared. And then 1 squared we can just write as plus 1. So I would still try to factor this second expression, x squared plus x plus 1. I would be looking for factors of positive 1 that add up to positive 1. In that case, there's no integers that we can choose that will make this true. So this is what they mean by irreducible. We can't reduce this into two separate linear factors. It contains a quadratic factor. So that will make the setup a little bit different. Our first factor is still linear, non-repeated, so we'll just have a over x minus 1. Then our second factor that has the quadratic in the denominator, x squared plus x plus 1. The numerator will look like bx plus c. So we get some linear factor in the numerator involving an x with two unknowns. So you'll do that if you have some quadratic as a factor, as opposed to it being linear. If it's linear, you just get a constant on the top. If it's quadratic, you'll get some linear expression with two unknowns. So from this point, the rest of the process will follow as we've done previously. So let's multiply everything by the denominator on the left side and think about what will cancel. So we'll have just 3x minus 5 on the left. And then when we multiply on the right side, the a term, the x minus 1 will cancel, so that will pick up that quadratic factor. So we'll have a times x squared plus x plus 1. Then for our second term, the one that has bx plus c, the quadratic will cancel and we'll be left with x minus 1. So we'll have bx plus c times x minus 1. So let's first see, is there some numbers we can plug in that will allow us to solve for one of the unknowns? I see off the bat, if we plug in positive 1, this entire term will be multiplied by 0, and we'll be able to solve for a. So let's see what happens when x equals 1. On the left side, that will give us 3 times 1 minus 5. And this will equal a times 1 squared, which is 1, plus 1 plus 1. And that whole second term will become 0 due to being multiplied by 0. So 3 minus 5 is negative 2. And this will, a times 1 plus 1 plus 1 will give us 3a. So let's divide the 3 over, and we get a result for a. A should be negative 2/3. So let's hang on to that one. Then let's see, is there something else we can do? If we plug in 0 for x, that would delete the b term. And we do have a value of a that we can plug in. So if we plug both of those in, we should be able to solve for c. So let's say when x equals 0 and a equals negative 2/3. Let's see what we get. So this will be 3 times 0 minus 5 equals negative 2/3 times 0 plus 0 plus 1, so multiplied by 1, plus b times 0, so that'll be 0 plus c, times 0 minus 1, so times a negative 1. So 0 minus 5 on the left side, we'll just leave the minus 5. This will equal negative 2/3 minus c. So let's add the c over to the left side. I can go ahead and add the 5 over to the right side, so c should equal positive 5 minus 2/3. That positive 5, let's write that as 15 over 3, multiplied by 3 over 3. minus 2/3. So c should equal 13 over 3. So now that we know both a and c, let's plug those in and just choose some other value for x. Let's say 2. You can say when x equals 2, a equals negative 2/3, and c equals 13/3. So this will give us 3 times 2 minus 5 will equal negative 2/3 times 2 squared is 4 plus 2 plus 1 plus, now our don't know b yet, so this will be b times 2. You can write that as 2b plus c. We know c now as 13/3 times 2 minus 1. That'll just multiply by 1. So let's clean this up a bit. This will be 6 minus 5 on the left side. So that will leave us with positive 1. This will equal negative 2/3 times 4 plus 2 plus 1, so times 7, plus 2b plus 13/3, since all of that was just multiplied by 1. Okay, we can get rid of these fractions by multiplying everything by 3. So on the left side, that would give us positive 3. It will clear the 3 for that first term. Just get negative 2 times 7. This will become 6b plus 13. So we multiplied that whole equation by 3 on the left and right side. So we get that 3 is equal to negative 14 plus 6b plus 13. On the right side, negative 14 plus 13 will give us a negative 1. So 3 equals 6b minus 1. Let's add that 1 over to the left side. So 4 will equal 6b. And then divide both sides by 6. You can say b equals 4 over 6, which reduces to 2 over 3. So a little bit of algebra to make our way through. Just got to be careful with the fractions and negatives. But now we have a, b, and c. So let's write our result. Let me try to fit it in here. We started with 3x minus 5 over x cubed minus 1. We said this is equal to a over x minus 1. Let's try to keep these both on the screen. So our a value was negative 2/3. We can just write that as negative 2/3 over x minus 1 plus bx plus c. So this will be plus, our b term is 2/3. So 2/3 x plus our c value of 13/3 all over x squared plus x plus 1. So a little bit tricky with the fractions. But we were able to, again, just pick some values of x and plug that in, and then plug in our knowns once we found out what a and c were equal to. So this was a case of having a non-repeated irreducible quadratic factor. We had to add a term like this, where we have some linear term in x with 2 unknowns in the numerator. So our last case will be whenever we have a repeated irreducible quadratic. And just like before when we had a repeated linear factor, we'll just need to have multiple fractions that build up to our power. So we're given x cubed plus x squared, and this is over x squared plus 4 to the second power. So this will split. We have this irreducible quadratic. If it was x squared minus 4, we'd be able to treat that as a difference of squares, but we can't reduce this into some linear factors. So we have a repeated x squared plus 4, a repeated non-reducible quadratic factor. So we'll just need to make a first fraction with x squared plus 4 to the first power. And then the second fraction will have x squared plus 4 to the second power. And if this was cubed, we'd have another term, or however high the power is, that's how many terms we'll have. And in our first fraction, we'll have something that looks like ax plus b. And in our second fraction, we'll have something that looks like cx plus d. So in this case, we will have 4 unknowns that we need to find. So let's multiply everything by the denominator on the left side. It will cancel there, so we'll be left with x cubed plus x squared. Then for our first term, one of the x squared plus 4's will cancel, and there'll be one remaining. So we'll have ax plus b times x squared plus 4. And on our second term, the whole denominator will cancel, so that will just become cx plus d. So let's see if we can pick any values that will cancel every unknown except for 1. And in this case, it doesn't look like we'll be able to do that. There's nothing that we can plug in really that will cancel everything except for 1. We could plug in 0, and that will delete our a and c term, but we'll still have b and d. We would need to ultimately cancel 3 of them at once. So let's take that other approach where we multiply everything out on the right side, collect our like terms, and compare it to what we see on the left side. So we'll have to FOIL those first 2 terms. So that will give us ax cubed plus 4ax plus bx squared plus 4b, and then plus cx plus d. So let's group, we don't have any other cubed terms, so we just have ax cubed. We just have bx squared. Then we have 4 times a times x plus c times x, and then plus 4b plus d. So on our left side, we can write this as x cubed plus x squared plus 0x to the first power plus 0 for our constant term. Then we have ax cubed on the right side plus bx squared. Then let's factor that x out of the next 2 terms, so we can write this as 4a plus c times x, and then plus, as our constant, 4b plus d. So let's make our comparisons. The coefficient of x cubed is 1. So that means a should be equal to just positive 1. That's our only cubed term, so those coefficients must be equal. For our squared terms, we'll get the same thing. We have a coefficient of 1, 1x squared, and then we have bx squared here. So b must also be equal to 1. Then we have 0 times x on the left side. And on the right side, we have 4a plus c times x. So that means 4a plus c should be equal to 0. we already know a is equal to 1, so 4 times 1 plus c should be equal to 0. Then subtract the 4 over, c should be equal to negative 4. And then we have plus 0 for our constant term, so 0 should be equal to 4b plus d. And we know that b is equal to 1, so 4 plus d is equal to 0. And then we get that d is also equal to negative 4. So we have a, b, c, and d. Let's plug in to what we have written up top. We should get ax plus b, so a is 1. So 1x plus b, b is also 1, x plus 1, over x squared plus 4, plus cx plus d, our c value is negative 4x, plus d, d is also minus 4, so I'll say minus 4, over x squared plus 4 squared. So this was a case of having a repeated quadratic factor. We had this quadratic factor squared, so that produced two terms where we have the factor to the first power as the first term, and then to the second power in the second term. And then these two linear equations, or these two linear statements, with two unknowns above each one. So we've seen 4 different cases, and problems can have combinations of these. So we'll need to just look at whatever factors are in the denominator on the left side and see what rules we should apply in order to build the right side. So if it was just to revisit these, some non-repeated linear factors, if it's a linear factor, we just get some unknown over that linear factor. If in our second case, one was repeated, so we had a linear factor squared, we get two terms, linear factor to the first power and then to the second power. You just build up to however many powers you have. And then for quadratic factors, in this case, we had to put this linear expression with two unknowns in the numerator instead of just a or b. And then the process from there to solve is the same. We just have to choose maybe some values of x or multiply everything out and compare the terms, the coefficients on the left side and the right side. So that'll complete this section. We had those 4 different cases. So this will be a useful skill later on in a calculus course. This will come up in the middle of maybe an integration problem. It might be beneficial to re-express some fraction like this, where you have these multiplication of factors into a bunch of separate fractions. There'll be some that can tend to make the problem easier to solve if we can decompose some fraction into a bunch of separate fractions. Okay, that'll be it for this video, and I'll see you next time.